Hello, you all back with some more linear algebra, and I'll jump straight into where we left off before. So we're in chapter 6, section 4. We're looking at the Spectra theorem, the proof of that. We just finished confirming that b has to equal 0 and a minus ai x equals 0. So that would mean that lambda equals a equals a real number, and x equals a real eigenvector. So now we proceed to proving the second part of the theorem. All right. So we have that lambda 1 be an eigenvalue of A, and Q1 is the unit vector that is an eigenvector with eigenvalue lambda 1. So basically all we did was take the eigenvector divided by its magnitude to get the unit vector. Right? And we'll choose V2 all the way to Vn to be an orthonormal basis for span Q1 perpendicular. What then is the matrix for the linear transformation UA with respect to the new orthonormal basis Q1 V2 Vn equals the orthonormal basis. We're saying UA equals B equals lambda 1 and a bunch of zeros, it seems. There's an asterisk here, and C seems too abstract at the moment. And C is n minus 1, n minus 1. And it's saying that we're using a change of basis formula, which is B equals Q inverse A Q, which equals Q QT A Q, because Q is an orthonormal matrix. Therefore, BT equals Q inverse A Q T equals QT A QT they're saying that this equals QT AT Q, which equals QT AQ, which equals B, since B is symmetric. So since B is symmetric, A equals AT. Since B is symmetric, we deduce that the entries asterisk are all zeros and that C is likewise symmetric in Rn minus 1 symmetric. We now consider the n minus 1 cross n minus 1 symmetric matrix C, a unit length eigenvector of C in Rn minus 1 corresponds to a unit vector Q2 in the n minus 1 dimensional subspace span Q1 perpendicular. Continuing this process n minus 2 steps further, we arrive at the orthonormal basis Q1, Qn consisting of eigenvectors of A. So I hate the highly symbolic nature of this, but there's an example coming up. So let's focus on the example. So we have symmetric matrix. Zero, 1, 1, 1, 1, 0, 1, 0, 1, and AT equals, just to show the process, 0, 1, 1, 1, 1, 0, 1, 0, 1. So we see that the symmetric matrix AT does equal A. Right? So looking at the pattern, this has to be the same. This has to be the same. And then the corner doesn't really matter because it's the corner. So in order for it to be symmetric, it has to be symmetric about those axes. All right? So now let's find the characteristic polynomial. So AX equals lambda X for it to be an eigenvector eigenvalue. So this matrix simply scales the vector by that value, which makes this lambda the eigenvalue and that X the eigenvector. So AX equals lambda I X, which makes the lambda into a matrix. So now we can do some like that. And then we can say A minus lambda I X equals 0. And in order for us to have a non-zero null space, the determinant of a minus lambda I must equal 0. So because if the determinant of a minus lambda I is not 0, then the only way we can get a null space of that matrix is for x to equal 0. If we want a solution, a null space that's not the 0 vector, the determinant has to equal 0 as a property of determinants. So we can say determinant. Now we want the determinant of 0 minus lambda 1, 1, 1, 1, 1, 1 minus lambda 0, 1, 0, 1 minus lambda. So that equals 0 minus lambda, 1 minus lambda, 1 minus lambda, plus 0, plus 0, minus 1 minus lambda, minus 1 minus lambda, and minus 0. And I'm just checking the math on this. Right? So that equals 1 minus lambda, 0 minus lambda, 1 minus lambda, minus 1 minus 1. So that equals 1 minus lambda, 0 minus lambda, 1 minus lambda, minus 2. That becomes 1 minus lambda, 0, minus 0, minus lambda, plus lambda, plus lambda squared minus 2. So that equals 1 minus lambda, lambda squared, minus lambda, minus 2. So that equals 1 minus lambda. And then we have lambda minus 2, lambda plus 1. So this would be the characteristic equation. But, well, I guess all of these is a characteristic equation. So P equals 1 minus lambda, lambda minus 2, lambda plus 1 equals 0. Right? Let's see how this looks. I noticed that the book adds another negative and says negative lambda minus 1. I'll say negative lambda plus 1, lambda minus 1, lambda minus 2. So the negative comes from this here. So the negative comes out, the lambda becomes positive, and the 1 becomes negative. So this is the characteristic equation as the book has it. So therefore, lambda 1 equals negative 1, lambda 1, 2 equals 1, and lambda 3 equals 2, right? So now we can solve for the vectors. So if lambda 1 equals negative 1, then we have 1, 1, 0, 0, 2, 0, 1, 0, 2. Now we're finding that null space vector that does not equal 0. So I can say x1 equals negative x2, 2x2 equals 0, and x1 equals negative 2x3. So x equals 0, 0, 0, right? So I must have did something wrong. Sure, let's see. Right, so I must have added this matrix incorrectly. Let's be a bit more careful. So 0 minus negative 1 is 1, 1, 1, 1 minus negative 1 is 2, 1, 0, and 1 minus negative 1 is 2. And it's going to be the 0 vector on the right side. Yes, I left off something the first time. I don't remember what it was. So we can say x1 plus x2 plus x3 equals 0. So x1 equals negative x2 minus x3. We can say that x1 equals negative 2x2 and x1 equals negative 2x3. So a lot of different values for x1. So x2 equals negative 1/2 x1 and x3 equals negative 1/2 x1. So x equals x1, x2, x3, which equals negative x2 minus x3 and negative 1/2 x1, negative 1/2 x1. So that equals we have x1 equals those. So perhaps it was best to so this will be 1/2 x1 plus 1/2 x1, negative 1/2 x1, negative 1/2 x1. So this will be x1, 1, negative 1/2, negative 1/2. So if x1 equals 2, x1 equals 2, negative 1, negative 1. So the book got the same vector, but their negatives is different. So to keep it like the book has it, I'll say x1 is negative 2. So this would be negative 2, 1, 1 to keep it the same. So that's where lambda equals 1. Lambda 2 equals positive 1. So that becomes negative 1, 1, 1. 1, 0, 0, 1, 0, 0. So initially, since these are linearly dependent rows, we could zero one of those out. And we can also use row 2 to zero this row out. So now we have x2 equals negative x3 and x1 equals 0. So x equals x2 equals 0, negative x3, x3. And to keep it like the book has it, the book has x equals x2 equals x3 equals 1. So x2 equals 0, negative 1, 1. And for lambda equals 2, we have, let's see here, negative 2, 1, 1, 1, negative 1, 0, and 1, 0, negative 1. So x1 equals x3 equals 2x1 minus x2, x1 equals x2, and x1 equals x3. So maybe I did something on my matrix again. Let's see. I'll copy it down this time. So 0 minus 2 is negative 2, 1, 1. 1 minus 2 is negative 1, 1, negative 1, 0. And 1 minus 2 is negative 1, 1, 0, negative 1. That seems correct. I just picked a bad way to try to solve this system. So let's say we can make it work like this. So this will mean that x1 equals 2x1 minus x1. So x1 equals x1. Well, that doesn't help too much. Plus x1 is a free variable. So I guess everything here is a free variable. That's what that means. X1 equals x1. X2 equals x1. X3 equals x1. So if I just made that x1 equal 1, this will be 1 equals 2, 1 minus 1. That's right. 1 equals 1, 1 equals 1. All right, so that works. So the third eigenvector is 1, 1, 1, which does match what the book has. So x1 equals negative 2, 1, 1. X2 equals 0, negative 1, 1. And x3 equals 1, 1, 1. And the span of the spaces, E negative 1, is spanned by this vector, E1 is spanned by this vector, and E2 is spanned by this vector. Right. So that seems to be all of our characteristic equation, our eigenvalues and eigenvectors. Everything is there. And let me oh, it's not filling as well in the screen. I don't know, maybe I changed some settings somewhere, but all right. So now what we're going to do is these three vectors form an orthogonal basis in R3, so we can easily obtain an orthonormal basis by making them unit vectors. So Q1 will be x1 divided by the magnitude of x1, which equals 1 over 4 plus 1 plus 1, 1 over square root of 6, negative 2, 1, 1. Q2 equals 1 over square root of 2, 0, negative 1, 1. And Q3 equals 1 over square root of 3, 1, 1, 1. So these are the orthonormal vectors. They're vectors that point in directions that span R3. They all point in different directions, which means that the dot product of any three of them would be 0, any two of them would be 0, which we can check very easily. So that works. So x dot xi dot xj equals qi dot qj equals 0. So they're all right angles to each other. And now the bottom one is also unit vectors, unit. Therefore, the orthonormal diagonalizing matrix Q equals, just putting these vectors into uh, uh, a matrix form. So this will be -2 over square root of 6, 1 over square root of 6, 1 over square root of 6, 0, -1 over square root of 2, 1 over square root of 2, 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. And that is the uh, matrix, the diagonalizing diagonalizing matrix, such that diagonal equals Q inverse AQ, because AQ equals Q diagonal. So diagonal, so that basically the Q is in the middle, the matrix on the outside, diagonal on the other outside, so the chevrons on the outside, and we bring the Q to the left, which makes it inverse on the left side. Thus we have that. So we finish with this example here. I'll come back later and we'll take it from there and finish this section. See you then.